hard organisers of this symposium. I think the last few minutes is probably a plot by the Shell company. A rather clever gentleman that I discussed some of this work with some years ago, which really deals about the mechanism of the Fischer-Tropsch reaction on cobalt catalysts, said that we would probably know the true mechanism by the time that the last cubic metre of the Earth's natural gas resources were converted to diesel fuels by the Shell distillate process. I'd like to tell you that I've proved this guy wrong, but I'm not so sure about that. What I'm going to tell you is probably just another complicating feature in what is really a very complex reaction. Let me just remind you about the major features of the carbide mechanism, if you like, which has gained some popularity over the last few years. It basically consists of the steps that I've shown up here, and I guess this is a scheme which was published by Alexis Bell in one of his papers. It basically consists of the interaction of molecular carbon monoxide with a catalyst site, marked by a little asterisk, to give absorbed CO. The absorbed CO interacts with a second catalyst site, and the dissociation of the CO takes place into carbide and an oxide form of the catalyst. The oxide form of the catalyst is reduced back with the formation of water by its reaction with hydrogen, or perhaps by its reaction with carbon dioxide. The carbides, which are on the catalyst surface, react with hydrogen, which may be either molecular or perhaps atomic, to give the basic building blocks for the polymerization reaction, which I've called CHX here, where X may, for example, be 2. Now, I have a real problem with this reduction reaction here, because the reduction of carbon dioxide by hydrogen generally requires much higher temperatures than you need for the synthesis reaction. And although you could argue that you're really reducing surface oxides here, it is also true that the reaction of water, which of course is a major product of a Fischer-Tropsch reaction, with metallic cobalt in a fairly finely divided form, is more likely to go to the hydrogen route rather than as indicated by this equation here. Nevertheless, this is the popular mechanism of the decade, I suppose. There is no doubt that many people have shown that the carbides are highly reactive with hydrogen. I'll come to their reaction with water in a minute. There exist at least several different forms of carbides and different catalysts, and the different forms react differently. And I don't want to give all the references to this sort of work here. The reaction that I'd like to look at with you today is some work which we've done on the reaction of the positive carbide on a cobalt catalyst with water. This was first reported by Rava et al. Way back in 1980, and I believe the people at that time were working for Union Carbide, who proposed the stoichiometry shown here, and in fact were developing a commercial process for making synthetic natural gas from waste gases containing CO over a cobalt catalyst. And this was basically the stoichiometry that Rava and his co-workers determined for the reaction. The traces of C2 were really traces in very, very small amounts. Our own study of this reaction goes something like this. We were using a cobalt catalyst promoted with thorium and magnesium oxides in this sort of ratio here. We deposited our carbides on the catalyst at 203 degrees. We measured the amount of carbide by the CO2 which was formed in the reaction. Typically, over the whole set of experiments that we did, the amount of carbide deposited was about 2.31 millimoles. We then reacted these 2.31 millimoles with a steam strip of 50 millimoles of water, but we passed the water over the catalyst bed diluted with helium at various rates. The gas was collected, the products were collected in the gas bag and analysed by GSM. started, we began to realise that this was a much more complicated business than what Rava had first suspected. I'll just show you a typical product analysis here from a run, in this particular case where we used a stripping temperature of 223 degrees with 54 millimoles of water and just over a litre of helium. The amount of carbide deposited was 2.50 millimoles of carbide. The hydrogen strip was 53 millimoles, and this basically is the composition of the exit gas. And the first thing that you notice is that you form large amounts of hydrogen. In fact, hydrogen is the single most important product. In this particular case, 1 millimole of CO2 was formed and only less than half a millimole of methane. So we're not seeing anything like the stoichiometry that Rava reported in his work. A small amount of ethane and only traces of CO. Now it's less than 0.002 millimoles. This is just the detection limit of our GC. The carbide strip represented 63% of the total which was present on the catalyst. We then stripped the remaining carbide with 45 millimoles of hydrogen. The exit gas had this composition, 0.01 CO2, and the methane, 0.86. Again, a small trace of ethane, giving a total carbide recovery of 2.48 millimoles, or 99% of what was deposited. So that all looks very reasonable. When you look at the evolution of the major products, methane, CO2 and hydrogen as a function of time, this is an online analysis done with a mass spectrometer, you see curves which are very similar, like which this illustrates, and you see immediately that there is something very strange going on here because the major products all form at different rates and at different times. This became a little bit clearer when we began to look at the effects of space velocity of the stripping reaction on the CO2 and methane yields at various temperatures. And I'd like you to focus your attention at the highest stripping temperature here of 252 degrees centigrade. You will see that you see the 1-to-1 ratio of methane to CO2 only at very low linear velocities at this temperature. As you increase the space velocity of the stripping reaction, the CO2 yield remains quite constant, but the methane yield is falling away. And this really is a very strange result when you begin to think about it. Because what it really means is that the rates of CO2 formation and the rates of methane formation are quite different, which really implies that there are two pools of carbide present on the catalyst surface, one giving methane and one giving the CO2. And the question is, how does the water distinguish between them? You get somewhat similar results at lower temperatures, although here there is a slight decline in the yield of CO2 as you increase the linear velocity. We can plot these results in a somewhat different way again. And I might add that I'm only showing you selected bits of the results. In fact, there are many more very similar curves. This is now showing here the ratio of CO2 as a function of the total carbon-containing products as a function of stripping temperature and of various linear velocities. And you can see that only at low linear velocities can you get a ratio of 0.5 for that ratio. But quite obviously, as you increase your linear velocity, you can approach that ratio if you go to high enough stripping temperatures. Okay, let's look now at the effect of linear or space velocity on the hydrogen formation. One possible reaction which could give rise to hydrogen is this one here, the reaction of carbide with water with CO2 and hydrogen. And this represents the yield of hydrogen calculated according to that equation using the CO2 yields which we've analysed. And you can see the rate of hydrogen formation is falling off slightly with space velocity. However, this is now a comparison between the observed hydrogen yield, this is the total hydrogen yield which is in our gas bag, curve 2, and the yield calculated according to the equation on the freezing overhead. And you can see that we're forming quite a bit of extra hydrogen here. This extra hydrogen, we believe, is coming from the oxidation of the metal catalyst, the cobalt metal, by the water that is formed, that is present in the system. So we see here a reversal of the equation which is supposed to regenerate our catalytic active site. These were really the two major experimental observations which we tried to interpret whose interpretation I'm coming to in a minute. But we performed one further experiment in which we tried to strip the carbide with D2O. The experiment was something like this. We deposited 2.37 moles of carbide on the catalyst surface, and we stripped this partly with deuterium oxide at 203 degrees. We then purged our reactor with helium, and the remaining carbide was stripped with hydrogen at the same temperature. And the result was somewhat surprising. We recovered 2.76 moles of deuterium, of which 36% was there as HD, 5 or 6% was CH3D, 8, nearly 9% of this species here, 19% is CHD3, 30% is CD4. And this deuterium, this 2.76 moles of deuterium, came when we stripped the remaining carbide with hydrogen. So the obvious conclusion is that there is a large pool of hydrogen, or in this case deuterium, which is present on the catalyst surface and which is held very tenaciously. And this is of course quite consistent with some work by Bell and Winslow back in 1985, and consistent with what many other people have been saying here this afternoon about the tenacity of these catalysts, of these metals, in maintaining hydrogen in their structure. Let us look at these results again. And these are the major conclusions. For the reaction of carbide with hydrogen at low space velocities, exactly equal amounts of methane and CO2 are formed. The CO2 is formed rapidly and the CH4 slowly. That arises from the difference that the linear velocity of the stripping this gas has on these two species. And the interpretation which we've come to is that the water splits the carbide pool on the catalyst into two equal parts, one of which gives you a CO2 and the other one gives you water. And there are at least two possibilities in which this could happen. One is shown schematically here in this reaction. The water simply reacts with two carbides to give you two species, A and B. Now, for a whole variety of reasons which I haven't got time to go into here, we believe that this first one is simply not able to account for the results that we have. What we think is that something like the second one is in fact what is happening. And that goes something like that. Two carbides react with two waters and give us
two molecules of a species A dash. And this A dash, or these two molecules of A dash, can disproportionate to give, in a rapid reaction, CO2 and hydrogen. And in a much slower reaction, this intermediate B dash here, which subsequently reacts slowly with hydrogen to give you methane. Now the obvious interpretation of this B dash here is that it's in fact CH2 sitting on the catalyst surface. I'll come back to that in just a little minute. The hydrogen results, we interpret along these lines here. Firstly, it is quite obvious that water can oxidize the cobalt surface because we're forming such large amounts of hydrogen from the reaction. The deuterium, the use of the D2O strip, clearly shows that there are large amounts of hydrogen which are strongly absorbed from the catalyst surface or perhaps in the catalyst structure. And the implication of these results is that this reaction sequence here, where hydrogen is able to regenerate the oxidized form of the catalyst, may not happen in this particular way. And one way of getting around this apparent dilemma is to simply assume, as was done earlier in the Fischer-Tropsch history, that the reduction of the CO by hydrogen in fact goes via an oxygenated intermediate, and that this intermediate here is the one which disproportionates into carbide and CH2. Let us have a look at the nature of this species COH2, which I'm proposing as an intermediate in the reaction, from the point of view of being associated with a metal which has a high affinity for hydrogen. And what you might do, or what I'm proposing, and we can argue about it if you like, is that this species COH2 on the catalyst surface can in fact undergo these kind of equilibrium reactions with respect to the metal surface. So that in the extreme case, this species here is simply CO absorbed on a highly hydrogenated metal surface. If we accept that, then the disproportionation of this species here, there should be a 2 in front, really becomes the disproportionation, or if you like, the Boudard reaction, of CO absorbed on a highly hydrogenated metal to give the carbide sitting on a hydrogenated metal surface. Right. This species here, which I can rewrite as this here, which is our normal CH2 building block sitting on a cobalt surface. We're all in this reaction up here, of course, we're also forming CO2, and then this species here can react slowly with hydrogen to give us CH4. Now you'll see that the disproportionation of this species here then gives us our observed stoichiometry of 1 molecule of CO and 1 molecule of CH4 when we do the reaction slow enough, or if you like, at low enough linear velocities. Now, how can we incorporate this into a mechanism for the Fischer-Tropsch reaction over cobalt? We start off here with absorbed CO on the metal surface, on the cobalt surface, which everybody agrees happens. There are several different reactions which this absorbed CO can undergo. The first and most obvious one is that it can hydrogenate to this oxygen-containing intermediate, which can be in equilibrium, if you like, with this ketone structure. And as I said before, this is simply CO absorbed on a hydrogen-containing metal surface. Another reaction, and which is Most likely, in the case where you're running the reaction under extremely hydrogen-lean conditions, is that the CO simply disproportionates to the normal Wood-like reaction to give you a carbide. And this carbide can now react in two ways. It can react with hydrogen, or it can react with water, which is the reaction that we've been studying here. And the reaction with water, of course, gives us this intermediate again on the surface. The carbide can also be directly hydrogenated by hydrogen to give these intermediates sitting on the catalyst surface here. This is, of course, also a well-known reaction. This intermediate here, under normal synthesis conditions, that is, large amounts of hydrogen present in the system, can directly react with hydrogen, eliminating water to give us our basic building blocks for the polymerization reaction. Alternatively, if the hydrogen concentration in the reacting system is fairly small, it can disproportionate to give us CO2 and the CH2 or CHX intermediate, which of course has been the main subject of my talk here. So what we're really proposing here is that the oxygenated intermediate in the Fischer-Tropsch reaction may be there at very low concentrations and may in fact only be a kinetic intermediate, can in fact be viewed, if you like, as just another example of absorbed CO sitting on a highly hydrogenated metal surface. The main building blocks for the polymerization reaction are these species CHX here, if you like, and notice that I've drawn HX associated with the metal as well, because I think the actual nature of the distribution, if you like, that is sitting on the metal surface here will depend on the hydrogen pressure and the amount of hydrogen that is actually present on the catalyst surface. So you have this delicate balance of a series of equilibrium reactions, and your system can really respond in a number of different ways depending on your hydrogen partial pressure. So this is our current model, which I think really incorporates or synthesizes, if you like, the two major models for the Fischer-Tropsch mechanism, which has been around, namely the carbide mechanism and, of course, the oxygenate mechanism, which was proposed way back in the mid-50s. I thank you for your attention.
Let's Leiden. Some years ago, Mr. Araki made a simple experiment. He took nickel surface, deposited carbon on it to certain coverage, and then he offered this surface to a mixture of CO plus H2. He has seen that CH4, as a simple hydrocarbon, was much quicker, faster formed from the deposited carbon than from any other oxygen-containing intermediate. Later, Sackler Jr. made the same experiment with cobalt. Now my question is, what do you think that these gentlemen did wrong, that you ignore that evidence and suggest a mechanism which has been actually rejected by those experiments?
Well, I don't think they did anything wrong. Far be it from me to say that somebody did something wrong. I mean, we were drawn to this kind of mechanism from our observation of the reaction of carbides with water, which appeared to split the carbide pool into two equal components. And this is the only explanation that we could think of for that observation. Now, I think the gentlemen that you were referring to were not aware of this particular phenomenon.
In actual Fischer-Tropsch synthesis, you usually obtain the CO2 only with the iron catalyst as a reaction product, and not with the nickel and the cobalt usually. And in so far, I think if it were a general explanation, this system, then one should obtain the CO2 also with the other catalyst, not only with the iron.
I make no pretense that these suggestions that I put up here apply to iron and nickel catalysts. I think the nature of the carbides in iron in particular are quite different from what they are on cobalt, and it may very well be that there are in fact different mechanisms, if you like, of the Fischer-Tropsch reaction on different metals.
Cal Bartholomew, BYU. I wanted to offer a couple of suggestions or possible explanations, since you said these were the only ones you could think of.
Sure.
I wonder, under these conditions with such a high partial pressure of water, you mentioned the possibility that cobalt would be oxidized. Is it possible that the oxidized cobalt surface acts as a water gas shift reaction, water gas shift catalyst, thus producing hydrogen, and that the slow production of the methane occurs by another mechanism which was recently shown to be operative in cobalt alumina and nickel alumina catalysts, where you get formation of a methoxy or formate species on the support, which then can decompose to form a methane.
You know, the first, well, what we were doing in our experiments was this route here.
And you were hitting it with water.
We were disproportionating Ca on the surface to form carbide, and then we were reacting the carbide with water about through here.
Yes, I know.
That's what we were doing.
But
now,
when the water absorbs on the catalyst, it's possible that you could produce both. You could produce some carbon monoxide at that point, couldn't you?
well,
Which reacts immediately.
even at the highest linear velocities, we never saw any carbon monoxide.
Yeah. But it could react immediately with.
Now, let me just finish, right?
Yeah.
In a normal synthesis, what you of course do is this here, or straight through, right? So the comparison of what we were doing and what happens in the normal synthesis really depends on the relative rate constants around this way and that way. And my intuition would be that if you have hydrogen around, this is the favourite route for the reaction. Right? So the system, if you like, accommodates itself to the relative partial pressures of hydrogen.
Well, there's just one more comment. I just wouldn't anticipate that under these circumstances that you would have a hydrogen-loaded system. You said that you thought there was a lot of hydrogen in the system.
In our experiments, we were very deficient in hydrogen.
Yes.
Right? So we're going around this route here.
But you were postulating a hydride system.
What I'm postulating is an equilibrium of this species here, which involves hydriding the metal surface if you haven't got hydrogen there to begin with. The affinity of the metal for hydrogen is so high, if you like, that if you haven't got enough hydrogen in your system, this species here becomes your hydrogen donor to the metal.
Well, I'd like you to think.
Some 1989, some Italian authors found that if you have a cobalt catalyst and you have coexisting oxide, cobalt oxide and cobalt together, depending on the ratio, you always have some alcohol formation. Now I'm wondering if you have an oxidized surface plus a metal surface together, is it not possible to find alcohol formation or some oxygenate formation? You see, you assume a kind of intermediate, which is oxygen-containing carbon, which might react in a way to form some oxygen. I wonder if you find some kind of oxygen.
Well, generally speaking, the amount of oxygenates in over a cobalt catalyst is very low when you run it with excess, the normal 2-to-1 hydrogen to CO ratio.
I wonder why you need a reaction of carbide with water. Isn't it more likely that water dissociates on the surface and supplies two components, hydrogen, which is in equilibrium with gases, hydrogen, and oxygen, which is under the conditions you use almost irreversibly adsorbed. If it is, as I say now, then one can very easily understand why the ratio of CO2 in the products is independent of the flow, because there is nothing like dissolving oxygen, while from hydrogen something dissolves in the gas phase, and at a high speed in the gas, it's removed from the reaction zone.
But that possibility had crossed our minds, but we could not see that that would give you an exact one-to-one ratio of CO2 and methane in your products at low linear velocity.
Two small questions, and I think I should decline. Thank you very much for your